Yeah. Okay, 5-10 minutes we'll wait so that let all the people join. Then it is another 3 minutes is there for us. Wait. Yes. Just I'll be back. Very much, sir. You can mute your audio video.
எனக்கு போடுங்க இதுயா இது சக்கவாடி திரும்பிச்சுங்க ஏழு அந்த புளி கொண்டு காய் கூட போட்டு வச்சிருந்தாங்க ஏன்னு எடுத்து வச்சுக்கிறாங்களா அது ஒப்பன் போட்டு போட்டு அது எண்ணெய் காயிலே ஆனா செக்க வாங்கி மாட்டான்னு போச்சுங்க
Dr. Kamachi, good evening, sir.
Good evening. Professor Balaya has come.
Yeah. He's there, sir.
Okay, welcome, Professor Balaya. Welcome.
Professor Balaya told that he has attended a few of your lectures.
Okay. Very good.
Maybe you know him. He knows you.
Yeah, I met something. Somewhere I met him in Chennai, I think. Yes.
Yeah.
Professor Balaya. He is in 2 devices, huh?
Maybe one is presenting, one maybe from system.
Okay.
No, somebody has to unmute me.
Oh.
You are not.
No.
I'm not able to unmute. I'm not able to add video.
No. We are able to hear you now. See your video also.
Video also.
Yeah.
I can't see. Okay. I can see.
Welcome. Thanks for giving the talk.
Thank you. I can see you now.
Thank you so much.
So what I will do is
I think again you are muted. You have to unmute.
Maybe some host is muting all because some noise was
okay, but
coming.
speaker they have to relieve, no? They have to speak.
Yeah.
some panelists, maybe he is using two devices. One device that is getting muted. Yeah, one device is muted, another device is not muted.
Maybe Dr. Natswarup.
You should not mute. He is muting the other one.
Hello. I think Professor Balaya is muted. Please unmute him. One second. Yeah. 5 minutes, okay.
Now, can you hear me?
Yeah, we can hear.
Hello?
Okay. Great.
Yeah, now okay.
Yeah. And just to check if this video is seen.
Actually,
Sir, you can share the presentation.
Oh, I
You
need
can.
to share.
Yeah. You please share the presentation. Like yesterday, share content.
Yeah. Screen.
So that's a lithium-ion cell, and I'm going to show you what we
Share content for entire screen.
Professor Balaya.
Yeah.
I have some other meeting at 4:30. I may leave.
No problem.
Okay. So thank you so much for giving this talk to all students in India.
Yeah, you are welcome. So wait a minute. I'm going to share now.
Yeah, you can share now. We can see the slides.
Yeah. Optimize for text and other things.
No. You see that rounds are there, no? Fourth or third round. There is one share content.
Yeah, this is the share actually.
Before that, you should just keep your PPT just opened and kept.
PPT is open actually.
Okay, keep that share content.
PPT is open. This is basically share content. And
Yeah,
the
click.
application or share screen.
Click. If you click no, then you can see screen there. With your PPT is opened.
Screen is there, but very small. No.
Yeah, click that. Just click that.
Okay.
Now it is coming. Go ahead. Just wait.
Can you see now?
Yeah, we can see now. Put it in view mode, no? Yeah. Yes.
Is it okay?
All. Yeah.
Yeah, fine. Yeah. It is fine.
Fine. Yeah. Now, can you also
video you want to play, right? Yeah, video also. Yeah, just click on.
click. Is it okay?
Yeah, click it.
Okay.
on seconds if I overcharge it.
Yeah, okay. It is also coming.
Okay.
Yeah.
So then I'm ready.
Yeah, you can go to the presentation, put in the.
So I think just
you can
1 or 2 minutes we'll start.
Sure.
You can already okay.
Yeah.
One is there. Yeah, people are still entering. Okay.
Because later they will unnecessarily disturb speaker.
Okay.
Just 4:10 we'll start. Just we'll wait for 2 minutes.
Sure.
Sir, Sukla is there. Yes. Dr. Rutresh is there today. Professor Dasa already joined.
Good evening, Professor Dasa and Dr. Rudresh.
No, they are muted. You cannot call it. They will not. You can only send a message. You can send a message. Everybody is muted now, except a few. I do not know. Dr. Dinesh Rangappa, you inform everybody to keep their mics in mute mode.
Yes,
few
yes.
few people are still keeping mic open.
Good evening, all. I would like to request all of you to keep your microphone muted, and video also you can mute after talk start. Please avoid a disturbance to speaker and other audience. Last time we had a lot of disturbance. With that, speakers will get annoyed or distracted. Kindly cooperate by muting yourself, and let us here
Tell the
to.
names. Atira, mic is on. Atira, and 2 devices are used. Please put up 1 device. And Dimple Datta.
Dimple Datta, Atira, please.
You tell all the names. Sarai Kumar, Sarayu Kakantwar, Manchunatha, Rajendra Prasad, Kumar Swami, Vinuta K. Vinuta, K. Vinuta,
Rajendra
Yas
Prasad, please
Verma,
mute.
Yas Verma, Vinuta Yas Verma, Shivakumar Swami, still their mic is on. Rajendra Prasad.
Yeah. Yashwarma, please mute your mic. Rajendra Prasad.
Sarayu Kakat Sarayu Kakat, Doctor. Dimple
Vinuta
Datta.
K, please mute.
Athira R, AR, Athira.
In this case, graphite. So if you connect a simple wire, the electron will flow through the external lead, allowing the lithium ions to move from one end to the other end. So these are two half cell reactions I have given. One refers to the cathode. This is LiFePO4, very famous material, which I will cover later. So if you look at a charging process, basically we are going to remove lithium. You can see lithium ion is removed, electron is removed, and then the final product is going to be FePO4. So LiFePO4 gives rise to FePO4 if you force the lithium ion and electron to come out. For that only we supply the electricity, DC electricity from the solar energy. And if you assume that you have on the other side, which is the anode, on the other side, if you assume that you have a graphite, these lithium ions and electrons generated from the cathode are now going to combine with the anode in order to form the final product LiC6. So these two are reactant, these two are the products. So this is the full cell reaction I'm writing here. LiFePO4 plus 6C gives you FePO4 plus LiC6. Most importantly, you should understand that Fe here, it is in 2 plus state. P is 5 plus, lithium is 1 plus, oxygen is 8 minus. So 5 plus, 2 plus, 1 plus, it is 8 plus, 8 minus. It's completely balanced. It's a neutral material. Now, when you extract lithium and electron, when you extract lithium and the electron from this particular material and convert it to FePO4, Fe, previously it was in 2 plus, becomes a 3 plus and 5 plus, so 8 plus and then 8 minus, charge balance happens. These lithium ions and electrons, now they run through the external circuit because of the charging process. They combine with this graphite C6 and then it forms final product LiC6. So if you look at this particular reaction, the forward is the charging process, the reverse is the discharging process. When I say forward is the charging process, for that you need electricity. The reverse is a spontaneous process, which means if you bring this material in combination with LiC6, automatically this material and this material is going to be formed. The rate at which it is forming depends on the resistance that is connected in the external circuit. That is nothing but your load. If you connect a copper wire, it will happen instantly. If you connect a slightly thicker resistive wire, then it will happen slowly. Then you are talking about what is the current that is flowing. If you connect a copper wire, you are passing a huge amount of current, very high C rate. You are transferring the charges extremely at fast rate. If you connect through a high resistive material, you are passing very, very low current. So that is where we will talk about C rate. I will talk about it later. The most important thing what I want to say is, if you bring this material and this material into natural chemical reaction, you see here, there is so-called Gibbs free energy involved of the product. This is the product, these are the products, and the reactant in the virtual chemical reaction that would occur if electrically neutral material, these are electrically neutral material, are brought into contact. So you need certain amount of energy, which is nothing but the Gibbs free energy for this particular reaction to happen. That is that is the energy which is the difference between the electrochemical potential between the cathode and the anode. That is nothing but E. In this simple example, I have given high potential and low potential. E is the difference in the difference in the electric field or voltage difference, potential difference. But this is also true in a electrochemical reaction given here. So for this particular reaction to happen spontaneously, there is a so-called Gibbs free energy of formation, which is the delta G. That is nothing but the difference between the electrochemical potential of the lithium in the cathode and the lithium in the anode. I will not go into those finer detail, but if somebody is very keen, they can talk to me later. So what is more important is we are looking at the delta G, which is the Gibbs free energy of formation of the reactant and the product. That decides the difference in the potential between the cathode and the anode. In this particular case, LiC6 and graphite I have taken, but you can also imagine FePO4 and LiFePO4, or you can take this product on the top and the reactant at the bottom. It is exactly one and the same. So this Gibbs free energy of formation is given by the difference between the electrochemical potential between the cathode and the anode times the amount of charge that is transferred. So this Q, as I told you previously, it is nothing but the product of the charges involved and the Faraday constant. So if I substitute, then I get very famous equation, what is called Nernst equation. Delta G is equal to minus N F times E. So depending on the difference in the Gibbs free energy of formation of the product and the reactant, you are going to generate so-called potential difference E. And the number of electrons going to be number of moles of electron going to be transferred from the cathode to anode or anode to cathode, etc. So basically, voltage is converted by a chemical reaction through this Nernst equation. This is the basics of so-called battery. So when you talk about a battery, you need to consider certain factors. I want to design a battery. So what am I supposed to consider? I should consider what is the voltage of the battery, single cell. Is it 3.6 volt? Is it 2 volt? Or beyond 3.6 volt, etc. The next one is ampere hour. This is so-called capacity. So every time you go to a shop and then buy a cell, the first thing you should see is the ampere hour. What is the ampere hour? Is it 1 ampere hour? Is it 3 ampere hour? So these days people are able to cylindrical cell 18650, which I will introduce later. Cylindrical cell can also give you up to 3 ampere hour capacity. And then energy is also very important, watt hour. So it's nothing but the product of these two. So voltage times ampere times hour. So nothing but watt hour, that is the energy. And then power. Power refers to at what rate you can charge, at what rate you can discharge. It's like this. You take a bottle and then fill water, and then the volume of the bottle is nothing but your capacity. And the rate at which you can fill this water, or imagine that you are dropping the water from the bottle, and then the rate at which you can drop this water outside, that is nothing but the power. The rate at which you can deliver this electricity is nothing but the power. And you should also ask yourself, what is the cycle life? Typically today, lithium-ion batteries, they are operable about 700 cycles to 1000 cycles. That is why you take your mobile phone, you can only use it for about 3 years, not more than that. But when you go for the electric vehicle and then station storage application, the cycle life becomes extremely important. You need to enhance the cycle life, because nobody wants to spend $1 million or $5 million just for 3 years usage. They want to use it at least 5 to 10 years of period. So cycle life is very, very important. Safety is extremely important, especially just now we talked about a large scale stationary storage system. If there is any accident, it's a question of $10 million, $20 million kind of thing. I want to recall an incident. I think it is LG. LG had a kind of fire accident. Each unit is typically about 1 megawatt hour. There were about 500 units withdrawn because of that. And each unit is typically about $3 million. So imagine 500 units of $3 million, what is the cost? So that gives you a rough idea of the huge amount of cost involved if safety is not properly addressed. And then cost of the battery system is also extremely important. You don't want to spend huge amount of per kilowatt hour. Right now, lithium-ion battery is somewhere about $200 US dollars. So you don't want to spend, $600 or $1,000 per kilowatt hour, because you are talking megawatt hour, 1,000 kilowatt hour, right? So you need to consider the cost also. So let me start with the lithium-ion battery. I have given you the basics of battery. So I introduced the Nernst equation, and then I have given you what are all the requirements. I'd like to touch upon lithium-ion battery. Lithium-ion battery has energy density in the range about 100 to 200 watt-hour per kg. You see, per kg, let us say this is the per kg of the lithium-ion battery pack. So you can typically, get maximum of about 200 watt-hour. That is the meaning of that. As I told you previously, it has a cathode which can supply lithium-ion. It has an anode which can host lithium-ion. It has electrolyte filled and then wetting both the cathode as well as anode. And then it has a separator which avoids shorting between cathode and anode. By chance, if you short these two, what will happen is the lithium-ion are transferred instantly, and then electron will flow through the external load instantly. That is nothing but shorting. So that leads to so-called thermal runaway. You don't want that. And hence the separator is introduced. Remember, the separator is a polymer layer, very thin polymer layer, 10 micron to 15 micron, porous polymer layer, which will allow the lithium ions to move from left to right or right to left. And the electrolyte, by definition, it cannot conduct electron. By definition, electrolyte can only conduct ions. So it can only conduct a lithium ion. If it is a sodium ion battery, it can only conduct a sodium ion. The electrons always flow through the external circuit. So as I told you, when imagine that you do not have a load here, you are going to charge. Charge means what? You take electricity from the solar panel and then connect it to this DC current, DC voltage, connected to these two leads. Then you are forcing the lithium ion to move from here to here. So LiFePO4 will become FePO4. The lithium ions come here and then electrons will move through this. Remember that why electron moves. First, of course, I must say the other way. Basically, electron moves and that compels the lithium ions to move. This is because of the charge neutrality. Every time you transfer, let us say 1,000 lithium ions from 1,000 electrons through the external circuit, you have to transfer 1,000 lithium ions for the sake of charge neutrality. In nature, every material has neutrality. So all the positive and negative charges are always balanced. I told you here, there are 8 plus charges, 8 minus charges. So that happens always. So when you transfer 1 mole of electron through this during the charge process, you are also transferring 1 mole of lithium ions, and then this Fe2 plus becomes Fe3 plus. So the product is FePO4. Now previously carbon was there, this becomes LiC6. So this is what is called the charging process. In the discharge process, what you do, you remove this connection, this is solar power, and then connect a load. Depending on the resistance of this load, firstly, electron will move from here to here. I told you already, it is a spontaneous process. So the moment you connect these two, it's a spontaneous process. Lithium ion will move from the anode to the cathode. That means the electron will move through the external circuit, and lithium ion will automatically move again because of the neutrality, charge neutrality. This has 95% efficiency. It has no memory effect. I can talk about this if there is time, but otherwise we will skip this. And this is a typical, this is what I explained to you. During the charge process, electron moves from the cathode to the anode, positive electrode to the negative electrode, and then lithium ion moves during the discharge process. The electron moves from the anode to the cathode, and then lithium ions moves from the anode to the cathode. I also have to introduce a few more terminologies. I told you this particular famous reaction a couple of times already, so you know already. So while I'm moving from left to right, it is called a charge process. When I'm moving from left to right, it is called discharge process. While I'm charging, that means I'm moving lithium ion and electron and converting it to FePO4. This is what is happening. This is the voltage profile. It's called the charge voltage, charge profile. Okay. Then when I'm reversing the process, so previously I was here upon charging, that means I got this material. This is the starting material here, and then the end material is here. At this potential, you will get FePO4. When I'm discharging, that means I'm starting from here at the same potential as is, and then imagine the potential drops immediately, and then there is a discharge voltage profile and comes down. There are a few things that you should take note. How many moles of lithium ion or electron I remove? I removed 1 mole. 1 mole, okay, 1 mole. Then If I'm inserting reverse reaction, means I'm going to insert lithium ion to this and then convert it to LiFePO4. If I'm inserting exactly 1 mole of electron and lithium ion into FePO4, now I call this efficiency, Coulombic efficiency. That means charge is basically Coulomb. Coulombic efficiency is 100%. But many times I will extract 1 mole. I may probably insert 0.99 mole of electron into FePO4. So I call the Coulombic efficiency is 99%. The second thing is you look at the difference. Look at the difference. The difference is so-called polarization. Ideally, you should get this dotted line. Your charge should be at the dotted line. Your discharge should be at the dotted line. That dotted line is nothing but E. It is decided by the difference in the Gibbs free energy between the product and the reactant. That is nothing but, this is theoretically speaking. But most of the time, you see the charge voltage is above and discharge voltage is below. That is mainly because of the internal resistance. Every time you have internal resistance, you always have some amount of loss defined by I square R. The higher the current, the difference will be huge. This difference will be huge. I square, it goes as square, right? So the smaller the current, that means at low rate of charging. If I am taking, let us say 10 hours to charge this and 10 hours to discharge this, I call that C by 10 rate, C by 10 rate. If I do this in 1 hour charging and 1 hour discharging, I call this 1C. If I'm doing this in 12 minutes charging and 12 minutes discharging, I call this as 5C. So depending on the charge rate, if I do very slowly, like 10 hours I take for charge, 10 hours I take for discharging, then the difference, that is so-called the polarization, difference in potential or the polarization is very, very negligible. Because as I told you, it goes as I square R. The lower the current, the I square R, which is the heat loss, is negligible. Whereas if I'm doing at 5C, high current, by the way, theoretical capacity is 170 milliampere hour per gram. But in this particular case, I'm showing you 1C. That means charging at 1 hour, taking 1 hour for charging and that is charging 1 hour. So my capacity is relatively low, 140 or slightly lower than that, because I'm doing it at a high C rate. So whenever we work with the high C rate, two things can happen. One is the capacity may come down from the theoretical capacity, 170 milliampere hour per gram. That is the theoretical capacity for this. And the second thing is the polarization may go up at a higher C rate because of I square R. So these are the two things which you should know, and you know what is Coulombic efficiency. This I already introduced you. Specific energy is watt hour. That is voltage times ampere hour. Then if you normalize it to per kilogram, I call this a specific energy density. Sometimes people will look at watt hour per liter, because many times when we work with a nanomaterial, the packing density is going to be so low, the volumetric energy density becomes very important. Watt hour per liter may be low when you handle nanomaterials for lithium-ion battery. Whereas most of the material commercially used now, they have high packing density, and hence one can put in the small volume 1 liter. One can generate our huge energy, whatever. So watt hour per liter is going to be very high if the packing density of the cathode material or anode material is high. Watt hour per liter is going to be low if the packing density of the cathode and anode material, typically nanomaterial, is low. You have to bear that in mind. And remember one thing, cathode material always have to operate at high voltage, and anode material has to operate as low as possible. Then the difference in voltage, this is the delta V, between the cathode and the anode is high, and hence the achievable energy density is also high. So somebody may ask, how do I achieve high energy density? One way is to choose high potential for the cathode and very low potential for the anode. I will give you a few examples as we move on. At the same time, one has to also improve the storage capacity, ampere hour per gram of the cathode or per gram of the anode. If you can increase the storage capacity, or if you can increase the difference in potential between cathode and anode, you can increase the energy density. So these are the fundamentals that you should be familiar with. Let me now move on to the so-called different storage systems. I'm going to touch upon different storage systems. Okay. Before I move on, I would like you to understand lithium battery and lithium-ion battery. These are the two different things. Many times at least starting students may not understand the difference. So the lithium battery is something which was originally introduced in the beginning in this field. That means they took lithium as the reference electrode and then a cathode or anode material. Cathode means you are going to basically, okay, I will say positive electrode or negative electrode. That's better. Positive electrode, and then this lithium as the negative electrode. People used to take. This particular concept, what is called intercalation concept, was first introduced by Stan Whittingham. Very early days, 78, 80s kind of thing, where he first showed that a given material like titanium sulfide can be intercalated. That means you can bring lithium ion and then electron through the external circuit, and these two can be stored in titanium sulfide, lithium titanium sulfide, giving rise to a potential difference of about 2 volt versus lithium. Lithium is the reference here. That concept, so-called intercalation concept, was first introduced by Stan Whittingham. That was the original contribution and the starting point of the whole lithium-ion battery evolution history. But when they introduced this, they only got 2 volt. This particular reaction gives you 2 volt. You know how this 2 volt is now coming. That's mainly because of the difference between the gift-free energy of formation between the TAS2 and the LiTAS2. If you take the thermodynamic parameters and then substitute that in the minus NEF, you will get E is equal to 2 volt. Then John B. Goodenough, that time he was working on numerous, extensively on oxide material. He introduced the first oxide material which can be used for extracting lithium and hosting lithium versus lithium metal. He replaced this titanium sulfide or titanium sulfide by lithium cobalt oxide, the first oxide material which was used for energy storage. In this process, this is not a host, this is a supplying of material. So he used that as a positive material. Then he started extracting lithium ion from here and then electron from here and then plating it here and then reversing the process, what it was stripping. Plating, stripping, plating, stripping. In this whole process, this is the reaction. So initially he removed 0.5 mole of lithium. Of course, you may wonder why only 0.5, why not 1 lithium? If you go beyond 0.5 lithium, this lithium cobalt oxide becomes unstable. So he formed this particular reaction by taking lithium cobalt oxide on one side and the lithium metal on the other side. This gives rise to close to about 4 volt versus lithium. Lithium is your reference here. So that was a great contribution because they moved from 2 volt to 4 volt, especially using lithium cobalt oxide. Then they faced, yeah, can somebody ask them to switch off?
Ashwani Kumar, please switch off your mic. Ashwani Kumar. Ashwani Kumar. Hello, Ashwani Kumar. Not sure whether you can remove this guy, Ashwani Kumar.
You can remove them. You have to remove them. Okay, so this was the first concept of so-called lithium battery, and then they faced the problem of so-called dendrite growth. Because when you remove lithium ion and plate it, strip it, do this numerous times, 50 times, 100 times, 200 times, or 300 times. What happened? The plating was not happening on the horizontally here. It was basically a vertical growth of the lithium plating, so-called dendrite growth. As I told you previously, there is a separator which is only 10 to 15 micron thickness. If you have a sharp needle of lithium metal because of the plating process, then what happened? There is a shorting between the lithium metal and the lithium cobalt oxide and the battery failed. There was thermal runaway. So that is where Akira Yoshino came up with the idea of so-called graphite. I would like to acknowledge that there were a few other people, including Rashid Yashami and I think also, if I'm correct, there are a few other colleagues who contributed to the graphite invention. But Akira was the one who very cleverly made use of it as an anode material against lithium cobalt oxide and formed so-called lithium-ion battery. In this case, what happened during charge process, electron moves through the external circuit that compels the lithium ions to go and get intercalated, lithium ion. And so this is what I told you. This is a shorting, I told you already. But in this particular case, when you take graphite, this particular so-called lithium dendrite growth is more or less avoided, I will also tell you there are extreme cases where you may still have dendrite growth, but almost 99.9% of the case situation, the dendrite growth on the graphite is fully avoided by controlling the chemistry of the electrolyte. So the lithium ions are intercalated, or lithium is intercalated into the graphite, so you form LiC6, and then during the discharge process you reverse, and that this is happening at least 700 times, 1000 times, and Sony commercialized this. This is how the evolution came from lithium battery to lithium ion battery, and hence these three people contribution becomes extremely important. The one who introduced intercalation chemistry, the one who introduced high potential oxide cathode material, the one who made use of graphite as an anode and then provided a full cell, a commercially viable full cell, which Sony commercialized. So these three contributions basically led them to get the Nobel Prize, which they highly deserve. So as I told you just now, I mentioned to you lithium cobalt oxide as cathode and then graphite as anode. You must also understand what are the charge profile during charging process. The voltage profiles during charging process. For the moment, you please consider only the cathode material. Forget about this anode. Take only the cathode material versus lithium. Lithium is the reference. That is nothing but the zero potential here. With respect to 0 volt, when you are charging, that means you are removing lithium ion from lithium cobalt oxide, lithium ion electron, sorry. This is the charge profile. It is going up like that. That is what is happening during the charging process of the cathode. Now, for the moment, forget about this cathode. Just consider only the anode. That means graphite alone. Only the anode was 3.7 volt. The maximum voltage you can go for charging 4.2, minimum voltage 3.0. The energy density is somewhere about 140 watt-hour per kg. Cycle life is about 700 life cycle, and about 1% cell discharge. Means if you charge and then leave it for a month, so you lose typically about 1% of the total capacity. High temperature, you can go up to 55 degrees centigrade, is good. Low temperature, you can go minus 20 degrees, it is good. You can go up to 10C. 10C means in 6 minutes you can charge, and 6 minutes you can, by the way, you cannot charge quickly, which I will explain shortly. You can discharge quickly. 10C, it is good, but environmental is not so good because of cobalt. Whereas lithium iron phosphate is an excellent material. You can see high temperature is very good, low temperature is good, high rate performance is acceptable. Again, discharging, the charging has some limitation, I will explain shortly. It has extremely very good safety and environmental conditions. And this being a three-dimensional material, you can see the high rate performance the best actually, I mentioned to you. One of the limitation of the lithium iron phosphate, you can see here, it has low operating potential versus graphite, it gives you 3.2 volt compared to, for example, lithium cobalt NMC cathode material versus graphite, which can give you 3.7 volt. This gives you 3.2 volt, this gives you 3.7 volt. That's what I mentioned here. See here, 3.2, 3.7. Because of the lower potential, the energy density also goes down, about 100 watt-hour per kg. That is what you should bear in mind. This is an extremely good material, but energy density is relatively low. Now, I mentioned to you in the last slide that you can't charge quickly, but you can discharge quickly. All these three material. Why? If you charge quickly, I told you previously what is called polarization. If the voltage is lowered because of the polarization, higher the current, I square R, higher the current, higher will be the drop in the potential. So the 0.2 volt will reach 0 volt in no time when you pass a high current. Anytime you charge, you must charge it very slowly in order to maintain this incertain potential at 0.2 volt, not more than that. On the other hand, you can discharge. That means you can extract lithium from LiC6 because you are forming LiC6 upon insertion. You can remove the lithium as quick as possible and insert it into lithium cobalt oxide or lithium iron phosphate or lithium manganite. Of course, you have to still bear in mind not to exceed this voltage. Because of course, while charging, as you know, your profile is going to be from here to here. So you will never go beyond this. Please remember, your profile is like this. See, the profile is downward, downward. So you will never exceed this voltage. So you are always on the safe side. This is one reason why most of your electric vehicle, you take typically 2 hours for charging. But discharging, that means while driving, you can accelerate the way you want. So I talked to you about so much about lithium-ion batteries, and then I would like to address so-called safety. Okay, when can a lithium-ion cell fail? Okay, I have cathode, I have an anode. When can a lithium-ion battery fail? By chance, if you do fast charging without your knowledge, there is a possibility that you may develop so-called lithium dendrite. It may lead to so-called inner shot, micro inner shot. Because of that, there can be a self-heating. So this on this side, I'm talking about basically time. On this side, I'm talking about temperature. So as you keep on doing this again and again kind of thing, there is a possibility for micro shot because of dendrite growth or for various other reasons. And there is a so-called self-heating. But if you wait for a longer and longer time, the first thing that is going to happen is the SEI decomposition. Why? If you go back to this, I mentioned to you about the SEI. See the SEI. This is a polymer layer, which is the most soft material in the whole battery device itself. That is the one first, that is the one which is affected, which is going to melt first reaction because of the heat accumulation. Now, if you further wait, the next soft material is the separator. Separator is going to melt. If you further wait for a longer time, then what will happen? The anode, which is the graphite, is basically exposed to the air because there will be more and more bulging and then there will be more and more crack. I will show you in the next video. If you wait further, the electrolytes start decomposing and the cathode also start decomposing. But there is a so-called safety. There is a safety limit. You can only wait until this point. That means until the separator melt. At this point in time, the temperature reaches so much and the time is reached so much, you must leave that place. You shouldn't be staying there. So if you stay longer, then there is an air exposure explosion. There is an air exposure of anode, electrolyte, cathode. Then it runs into thermal runaway. The temperature rises quickly. So I have a short video of this particular one, and I want you to have a feeling of how bulging actually. Now you can see that. Can you see now?
Yes.
Yeah.
The cell is visibly bulging. I can see it.
Yeah, the cell is visibly bulging.
Yes, because according to our checks, we're getting very close to overcharging.
Yeah. Can you see this? Now it's time for us to. Can you see this one?
Yes. Yes, we can see.
Okay.
Yes,
thank you. Yeah, thank you. So this is a kind of a short video where I want to show you if I deliberately overcharge. So that's a lithium-ion cell, and I'm going to show you what would be the consequence if I overcharge the cell. Bulging actually. Now you can see that. Can you see now?
Yes.
Yeah.
The cell is visibly bulging. I can see it.
Yeah, the cell is visibly bulging.
Yes, because according to our checks, we're getting very close to overcharging.
Yeah. Now it's time for us to move back. Move back.
So I see a bit of smoke. Oh my goodness.
Can you come? Yeah.
Imagine this multiplied many, many times when it's all in a pack.
All right. So I try to be back now. I think I should be back. Yeah. Can you see my slide now?
Yes, we can see.
Okay, great. So that is, I don't have time, but anybody can go to channel news ratio and then view the whole episode. this tells you if a single cell explodes, what is the amount of heat generation, thermal generation, and then fire that happens. That is just I want you to get a feeling for that. That's why we deliberately removed the BMS in that particular cell. So I tried to allow it to exceed the cutoff voltage purposefully. It is actually a lithium titanate as an anode and then NMC as a cathode. 3 volt is the upper cutoff volt. Actually, we can go up to 4.3 volt. 4.3 volt. You are right. 4.3 volt. And then I purposefully exceeded 4.3 volt, gone up to 6 volt in order to show you what could be a consequence. Actually, many batteries were getting exploded in Singapore when they were using it in PMD. You have seen the personal mobility device people were riding in the video, and the channel News Asia asked me what could be the reason. We could not figure out. We only felt that because of wear and tear, the BMS may be getting spoiled. If you purchase cells or charger from a poor quality supplier, I mean within quote poor quality supplier, and in that case this could happen, but we haven't confirmed it experimentally. So now we talked about so-called safety of a lithium-ion cell. I would like to move for so-called safe sodium-ion cell in the next 15 minutes. The objective of this particular sodium-ion cell is basically to address the microgrid, as I told you previously, particularly to address the intermittency issue. That means the storage system need not be very huge. It need not be 10 megawatt hour. It can be smaller size. It could be up to 1 megawatt hour. But it should have high rate of charging and high rate of charging in order to address the power fluctuation, intermittency. It should have a decent cycle life, at least about 5,000 cycle. It must be safety and it must be inexpensive. Of course, we could not do 1 megawatt hour being from the academic institution. So what I try to do is make 5 kilowatt hour pack with similar specifications, and then do a kind of demonstration, connecting it to solar power or connecting it to the microgrid or connecting it to telecom tower, whatever. And then if we are able to do so-called this particular demonstration, at least I can give a guarantee to the investor that they can confidently go from 5 kilowatt hour to 1 megawatt hour, 1,000 kilowatt hour. Of course, there is a question. Why we have to go from lithium-ion battery to sodium-ion battery? As I told you, I'm not. Okay. Somebody has to control them. Hello. Can you control them, please?
Please put your mic off. Done. Dinesh, done. It's done.
Yeah, thank you. So I'm not against lithium-ion battery. We do have a lot of projects related to lithium-ion battery, but there are some occasions where we feel that sodium-ion battery could be a good technology, particularly because of the geopolitical issues. Lithium resources are limited in Argentina, Chile, and then Australia, and maybe China, elsewhere. You do not want to rely upon 10 megawatt hour, that kind of large scale stationary storage systems on supply material, which are coming from this type of, particularly this type of, South America kind of thing. Politically, they may not be very stable. Of course, there are also advantages in terms of the cost. It could be cheaper than lithium-ion battery. It's plenty in seawater, so you have no limit on that. It cannot be cheaper also. And I would like to introduce 2 articles which we published. We have published several articles, but I just want to take only 2 articles. One is this particular one, where we introduce non-flammable glyme-based electrolyte. I'm going to show you the flammability test and then thermal stability of this so-called glyme-based electrolyte. Here, NaBF4 in tetraglyme. I'm taking a fire closer to the electrolyte and observing whether it is becoming flammable or not. As you can see, 5 seconds, 60 seconds, nothing happens. It doesn't catch fire. Whereas if I take a carbonate-based electrolyte, ECDMC, NaPF4, ethylene carbonate or dimethylene carbonate, 2 seconds, 10 seconds, it catches fire. Even diglyme for that matter. You can see 5 seconds, 10 seconds, it catches fire. Whereas tetraglyme is non-flammable. That's the first message. Second message is, if I take this electrolyte and look at the DSC, differential scanning calorimetry, you can see thermal events for the blue, which is the diglyme, that happens as low as 116 degrees centigrade. You remember previously I talked about the thermal event you see here, electrolyte electrolyte oxidation. So that should happen at very high temperature. If it happens at very low temperature, it is not good for you. Similarly, carbonate also has a thermal event as low as 135 degrees centigrade. On the other hand, the green one, tetraglyme, the major thermal event happens at 273. Of course, minor event happens at 250. It's a very thermally stable compared to these two electrolytes. And electrochemical window is also very important. I talked to you about electrochemical window. The solid one is the tetraglyme. That means you can go easily up to 4.7 volt without any difficulty. You can strip a plate and then strip sodium, and that is very clearly seen. So you can see that it is fully reversible up to 4.7 volt. The reference one is a carbon-based electrolyte. This is a reference one, carbon-based sodium perchlorate in ECPC as a reference. So both of them have very decent wide electrochemical window. And the conductivity is acceptable, not bad. If you compare 4.4 millisiemens per centimeter, that is for the carbonate-based electrolyte, we are getting about 1.3, which is still acceptable, not bad. And this is yet another important contribution from our side. I want you to let's take note of this and then read through that, where we introduced cathode material. Actually, it's the title itself is a comprehensive study on electrolyte, anode, and cathode for developing commercial type non-flammable sodium-ion battery. I would say safe sodium-ion battery. So we use sodium iridium phosphate as a cathode material. We also work on a number of oxide material, O3 type and P3 type, and a few other materials. Just now you saw PV, Prussian blue also. But in this particular presentation, for the next 5 to 10 minutes, I'm going to talk only about sodium iridium phosphate. You can see here 24 hours of stirring and then drying, and then pre-calcination and then calcination. And the paper that I'm mentioning here, energy storage material, gives you complete detail, even up to 3 kg per batch. So we get an acetone phase. The phase group is R3C. We are not considering sodium ordering. Some people talk about sodium ordering, but in our case, when we did refill fitting, we are not considering sodium ordering. So we fix this as rhombahedral unit cell, R3C. And this is the kiloscale lab where we are able to go up to even 5 kg per batch production. You see, this is a 200 liter reactor. The evaporation is done by many ways. This is proto evaporation, spray drying, or conventional oven, where I can put 200 liters of the this solvent directly and then evaporate. So we do variety of evaporation. And then we have so-called retort furnace. I can go up to 8 kg precursor. The final product will be typically about 4 to 5 kg sodium iridium phosphate. Of course, we combine it with the wet scrubber because there are also side unwanted organic component that will be evolved during the calcination process. So you have to scrub it so that you don't pollute the environment. And here I give you an example of pristine sodium iridium phosphate, 5 gram up to 3 kg. And you can see here not many impurity phases are introduced. The surface area is 31.6 meters square per gram. Tap density is about 0.74 gram per centimeter cube. On the other hand, we also did zinc doping in the place of vanadium, typically about 10% of zinc doping we did. That is that the charge is compromised by an increase in the concentration of the sodium, and hence the capacity will also increase. And you can see here 5 gram to 3 kilogram, and we don't introduce any substantial impurity. Acceptable impurity only is introduced. Interestingly, the surface area has come down with zinc doping, 20.6 meters square. Tap density has gone up. I mentioned to you volumetric energy density, watt-hour per liter. The higher the tap density, the higher will be the volumetric energy density. Now I'm comparing this pristine NVP. This is pristine NVP versus when a zinc doped NVP was against sodium. This is also called half cell. You know half cell. Huh? So as you can see here, 5 gram or 200 gram or even for that matter 3 kilogram, the discharge capacity doesn't vary significantly. These are the pristine NVP versus sodium. So typically we get about 82, you can see here 82 milliampere hour per gram at low C rate, at high C rate 67 milliampere hour per gram. But with zinc doping, you can see here, first of all, the capacity has gone up closer to 100. It's written here 100. And then even at 4C, that means 50 minutes charging and 50 minutes discharging, we get a decent capacity of about 91 milliampere hour per gram. So the capacity is improved and the rate performance is also improved. Most importantly, you see here, there is an additional reaction, which is because of vanadium 4 plus to 5 plus. In this case, vanadium goes from 3 plus to 4 plus. In this case, vanadium goes from 3 plus to 4 plus, and then 4 plus to 5 plus. There are extra redox reaction, and hence the capacity has gone up as shown here. This is the pilot line where we produce commercial type cells. This is very important. Why I am mentioning all these things, particularly to students, is when you come up with a certain ideas, it is always important to consider whether it is industrially relevant or not. You may not have facilities, but you can work with some of the institutions within India or outside India, that includes our lab, in order to consider this type of commercial type viabilities. So we have made this type of commercial type cells using sodium vanadium phosphate and the hard carbon as the anode. You can see here, this is using pristine NVP versus hard carbon. This is using modified NVP, zinc doped NVP versus hard carbon. I think both of them are zinc doped. I'm sorry for that. So I'm not comparing here pristine because I don't have much time. This is a charge process. You can see here clearly there is a plateau, which is because of the vanadium 4 plus to 5 plus. This is the discharge profile. So you get about 60 watt-hour per kg. When I say kg, it is a complete weight of the cell. We don't calculate this energy density based on cathode material and anode material. Many times people report that is acceptable. But when you talk about industry level cells, you have to all the time report only versus the complete cell. Here I am showing you different C rate performances. This is the low C rate. This is the high C rate. You see here, I can discharge close to about 5C. 5C is typically about 12 minutes per charging, per discharging. I can still retain 83% capacity as compared to low C rate. So very decent high C rate performance. And the cycle life also shown here, retaining 81% capacity up to about 800 cells, 800 cycles. So please remember, if you want to commercialize anything, minimum you should achieve 500 cycles. So in this particular case, 800 cycles. We have gone up to 1,000 cycles, but then the capacity retention is about 78%. We are still working to improve the cycle life close to about 2,000 to 3,000. Ideally, 5,000 cycles is the target. I would like to conclude at this stage. So as you know, I have introduced basics of energy storage system, talked a lot about lithium-ion battery, addressed safety issues, introduced non-flammable liquid electrolyte for sodium-ion battery. Actually, I have not shown this, but if you read our paper, you will understand clearly. We have shown stable ECSI layers on hard carbon anode. Doping of zinc in the vanadium site improved the rate performance as well as storage capacity as well as cycle life. Materials are scaled up from 5 gram to 3 kilogram. 18650 cells are eventually fabricated and tested. Alluvial doping of the site by zinc. Reduce internal resistance and actually these but it will be published subsequently. As you can see that this is time for me to stop. So I would like to show you that in the last few years, about 14 years of my stay, we have developed several key capabilities in NUS. This is also very important. As my colleagues, I see several of my friends are also participating in this webinar. So it is very important to develop certain capabilities which are compatible with industry scale, commercial level, commercial purposes. Kilo scale lab, pilot line. We are able to estimate the heat water. We are also able to analyze internal responsible for these heat losses. This is my acknowledgement. Several of my group members contributed to the sodium-ion battery research. The funding from Ministry of Education. Funding is also from NRF, National Research Foundation, also EMA, Energy Market Authority. With that, I would like to stop my presentation. And most importantly, I shared these type of details, commercial viability, etc., in order to kind of promote research amongst youngsters. Particularly think about publication. I'm not against publication, but at the same time also think about how useful your research for the industry, for the company. You may not do everything, even if you can do one component, whether it's a cathode or anode or electrolyte or separator or grinder. You can work with your colleagues and there is commercial viability. I'd like to stop here and then take.
Thank you, Professor Bhaya, for extensive presentation on basics and advanced application, and also providing, I think, sodium-ion battery in commercial level applications. So now the talk is open for discussion. So anybody with questions, please message. I will follow one by one so that you can ask questions.
Are there?
Yeah. I'll just if they put their questions, then I will call. Dr. Jivanand, if you are there, you can ask. He's asking about what is memory effect. Dr. Jivanand.
Okay.
Hello.
Yeah. Please go ahead.
Sir, Dr. Jivanand question, what is memory effect?
Yeah. See, there are certain battery systems. For example, lead acid battery systems. This type of battery systems, they remember to what extent you have charged in the previous cycle. If you are charging it to 50% of the full capacity, or let us say 60% of the full capacity, and next time when you are charging it to the 100% of the capacity, so you will see certain anomalies in your charge profiles at about somewhere about 60%, which is the effect of your previous charging. So-called memory effect. This is the inherent property of this particular battery system. Whereas lithium-ion batteries do not have this memory effect. That gives you an advantage. At any level you can charge, any level you can discharge. Today you may charge 40%. Tomorrow you may charge 100%. No side effects. No disturbances in your performance, in your charge profile, etc. That's what I meant by so-called memory effect. Memory effect is absent in the case of lithium-ion battery, whereas this is present in few other technologies like lead-acid battery is a very good example for that.
So second question from Chinna. Chinna is there. He's asking about, please explain what is charging mechanism of lithium-ion battery is, and when we charge our lithium-ion battery, where the current goes towards anode or cathode. How does the current initiate the first deintercalation and why?
Okay, so you are talking this 19.56. Is that the one you are reading? 19.56.
Yeah, maybe should be yeah.
19. Look at the chat. 19.56. If you are reading. Okay, so I mentioned to you while charging, if you take lithium iron phosphate as cathode, graphite as an anode, while charging, the electron will flow from the lithium iron phosphate to graphite. Lithium ion will flow through the electrolyte from the cathode, which is the lithium iron phosphate, to the graphite. And please remember always, it is the electron which is moving from the cathode to the anode, which compels the lithium ion to move from the cathode to the anode for charge compensation. This is very important that you understand that you need to have charge compensation. Because of that, lithium ions are moving from the cathode to the anode. It's the electron that moves from the cathode to anode first that initiates the lithium-ion movement from the cathode to the anode. I hope I answered that.
Yes.
If Tina can come, I can interact with him.
Yes, yes. You can contact Chinna, can contact directly Professor Bolaya. And the next question is from Libby Thomas. What is the difference between capacity and capacitance? Is difference between capacitance and capacitance? Capacity and capacitance is asking.
Okay. Basically, capacity and the capacitance are referring to the stored charge. Stored charge. Okay. Stored charge is basically ampere hour. That is the capacity. When it comes to the battery, we use the terminology stored charge, nothing but the coulomb of charge, ampere hour, coulomb, ampere hour, and then we talk about how many coulomb of charges are transferred from the cathode to the anode to the cathode. That decides you what is ampere hour. What is ampere hour capacity of the battery? When you talk about capacitance, that is that is the capacitance. That is commonly used in a capacitor. So in a capacitor, you have positive ions and negative ions, or positive charges and negative charges stored on both electrodes. So there you are basically storing the charge between two parallel plates, and then you talk about capacitance. There you talk about capacitance. So in the battery, we talk about capacity. That refers to the amount of charges being transferred from cathode to anode. In the capacitor, you still talk about the amount of charges stored on parallel plate. We call this as capacitance. I hope that explains.
Yes, sir. Yes. And one more question from same guy. Which one has better cycle life, sodium ion or lithium ion battery?
I want to say that both lithium-ion battery and sodium-ion battery must have long cycle life. If you are looking at electric vehicle, for example, Nissan Leaf, they use lithium manganite versus graphite. They are probably giving you about 3,000 cycles or 5,000 cycles. I do not know exact detail on that, because you would like to at least charge it 3,000 times kind of thing. Imagine 3,000 times roughly gives you about 8 to 9 years of long life, even if you charge it every day. But definitely you are not going to charge every day. You are going to charge once in 2 days or once in 3 days. So their cycle life could be typically about 2,000 cycles a day. Coming to the stationary storage application, where we are talking about 5,000 cycles or more than that. The reason is, if I am looking at the fluctuations, so you remember you have seen charging, I talked about the intermittency. That means in a day, in a particular day, you may be exceeding or you may be coming down compared to the average power generation. You may be exceeding, coming down, exceeding, coming down. These are all within 10 to 20% of the average power. So you are going to charge, discharge in a shallow range. In this particular case, the charge, the cycle life should be long, very long, 10,000, 20,000. But here it is within a narrow voltage window. Within a narrow voltage window. You are not going to 100% charging, 100% discharging. You are going to charge and discharge probably 20% up, 20% down, or 30% up, or 30% down. In this narrow voltage window, you are expected to have 10,000 cycles or 5,000 cycles, etc. The one I showed you, 800 cycle, that is 100% DOD, depth of discharge. That is why the cycle life is somewhere about 1,000 cycles, retaining 78%. We are still trying to improve. If we can achieve 2,000 cycles or 3,000 cycles with 100% DOD, that is excellent. So one cannot say lithium-ion battery has long cycle life, sodium-ion battery has long cycle life. One should say that both of them should have long cycle life. First information. Secondly, if you are working with graphite, there are limitations. Typically, people talk about 1,000 to 2,000 cycles. But I showed you lithium titanate as an anode material. If you are working with the lithium titanate anode material, in that case, the cycle life can be 10,000, 20,000, because there is no SCI. I mentioned to you previously, all these detail I covered already, but this question helps in order to go into the detail. There is no SEA formation on lithium titanate, and hence you can go up to 10,000 cycle, 20,000